Today on Guess What I Found Out? Two rocks. That's where this starts. Two rocks over 2,600 years ago that broke physics open and still haven't let it close. One was a heavy black stone that pulled iron without touching it. The other was petrified tree sap that, when you rubbed it on fur, picked up feathers and dust out of thin air. And for the next 2.5 millennia, the greatest minds in human history desperately tried to figure out how. The black stone was lodestone, a naturally occurring magnet. The petrified sap was amber. The Greeks had a word for amber electron. You can already see where this is going. Here was the problem. In a world where nothing moved unless something pushed it, these two rocks moved things without touching them. Action at a distance. It was philosophically intolerable. So the ancient Greeks did what humans do when they hit something inexplicable. They reached for the closest analogy that made sense. First analogy, life. The rocks had souls. They wanted to pull iron. This was a reasonable inference from observation. Second analogy, smell. Invisible particles like tiny keys fit into pores in iron. That's why iron was attracted, but wood wasn't. The elegance, tiny invisible keys fitting tiny invisible locks. Not crazy, just wrong. Now for the third analogy, suction. Drawing inspiration from medical cupping glasses, which created a vacuum to pull blood through the skin, people thought that lodestone somehow created a pull, a bit like negative pressure. And then the fourth analogy, wind. Chinese natural philosophers, you see, proposed an invisible breath, a life energy they called Kai, flowing outward from compass needles and acting on them at a distance. But, well, none of these explanations were quite right. Still, they were the best thinking available at the time. That's really worth sitting with for a second, isn't it? The world was changing rapidly, and so was our understanding of nature. The scientific revolution swept across Europe, bringing new methods, new questions, and a bold willingness to test old ideas. For the first time, observation and experiment began to take precedence over tradition and analogy. It was a turning point, really, a moment when curiosity and careful investigation started to reshape what people believed about the forces at work in the world. Then came the 1600s and William Gilbert, physician to Queen Elizabeth I. Gilbert was, well, done with analogies. He ran experiments. He placed magnets behind paper, behind glass, behind water. The force passed through all of them, unaffected. Wind would disperse, fluid would be blocked. Whatever magnetism was, it was none of those things. Gilbert called it a sphere of power, an orb of virtue, a field that surrounded the magnet and shaped itself identically at every scale. Not a substance being emitted, a shape in space itself. Amber's force, which Gilbert named electricus after the Greek word, behaved differently. Paper blocked it. Wind could blow it away. It acted like, well, something was flowing. Two forces, two different behaviours. They'd be kept separate for another 2 centuries. In 1729, Stephen Gray was doing what scientists do, which is mess around with things and see what happens. He rubbed a glass rod and charged a lightweight ball. Then he attached a wire between them. The charge travelled down the wire and the distant ball moved. The force flowed, like water in a pipe. Electric fluid, people called it. Not wrong as far as it went. It captured something real about the behaviour, even if it missed what was actually happening. And then, on a Tuesday evening in 1820, Hans Christian Orsted is demonstrating a battery to his students, and he runs a wire carrying current near a compass. The needle twitches, not toward the wire, not away from it. Sideways, perpendicular. It rotates around the wire in a circle. Moving electric charge creates a magnetic field, not a pulling field, a vortex spinning around the current like water around a drain. Electricity and magnetism, once thought separate, are actually the same force, just different expressions. Michael Faraday proved this by moving a magnet near a wire, no battery needed, and current flowed. The motion of a magnetic field creates electric current. The two can be converted into each other. Faraday visualized these as real lines of force, rippling through space like waves in water. Now, the story takes a fascinating turn with mathematics and light. Faraday's patterns could be described, even predicted, using mathematics. The challenge: find equations that captured how electric and magnetic fields moved together. Perhaps light itself was a wave rippling through these fields. Light, electricity, and magnetism, one grand phenomenon. The search for a unifying mathematical language had begun. James Clerk Maxwell took Faraday's intuition and built equations around it. To make the math work, he imagined space filled with tiny spinning vortices, separated by ball bearings for smooth transfer of rotation. Spin one vortex, the bearings turn the next one, and the disturbance travels. It was a mechanical model, not literally true, but mathematically productive. He worked out the speed at which a disturbance would travel through such a medium. The answer depended on two measurable quantities: the stiffness of the electric field and the inertia of the magnetic field. Both had, quite interestingly, been measured in labs for unrelated reasons. He plugged the numbers in. The wave speed came out to approximately 300,000 kilometers per second, the speed of light. Light is an electromagnetic wave, one force, one field, one unified phenomenon that had been masquerading as three separate mysteries for 2,600 years. Heinrich Hertz confirmed it in 1887. He created a spark on one side of his lab. On the other side, a separate loop of wire, completely disconnected, produced its own spark. The electromagnetic disturbance from the first spark rippled through space as a wave and induced current in the second loop. That is the first radio transmission in history, achieved by a man who was just trying to confirm Maxwell's equations and thought his discovery had no practical application. Hertz died at 36. The nature of matter, well, it's a story that stretches across centuries of human curiosity and experimentation. From the earliest philosophers pondering what everything is made of, to the discoveries that would reshape our understanding of the universe, matter has always been at the heart of the greatest scientific questions. As we peel back the layers, we find that what seems solid and simple is in reality composed of intricate structures and hidden forces. The journey of uncovering the nature of matter continues to reveal surprises, challenging our perceptions and deepening our appreciation for the complexity of the world around us. Now, here is where it gets genuinely strange, Curious George. By the late 19th century, mathematicians noticed that vortices in fluids behave remarkably like matter. They attract and repel each other, depending on their spin direction. They are, well, stable. A vortex ring, a torus looping back on itself, much like a smoke ring, is actually self-sustaining. It resists changes to its motion, which honestly looks a lot like mass. Plus, it carries energy in its rotation. Lord Kelvin, in 1867, proposed that atoms might be vortices in the electromagnetic field itself. Not particles just floating in a field, but the field looped. Then, by the 1990s, researchers following in Feynman's wake showed that a single photon, a light wave, looped into a toroid, matched the known properties of an electron. Charge, spin, mass, and magnetic behavior, all emerging just from shape alone. Now, here is your question for today. If matter is just energy in a stable loop, a vortex in a field, does the concept of a solid object actually mean anything? Drop your answer in the comments and tell me how you think about it. I really want to know whether this changes how the physical world feels to you. Because here's what the deeper investigation reveals. Atoms are, well, 99.999999% empty space. The nucleus is orbited by electrons. The nucleus itself is made of quarks. But quarks account for less than 1% of the nucleus's mass. The rest, more than 99% of what makes something feel solid and heavy, comes from the energy of the gluon field, the force binding the quarks together. Mass is not a thing you have. It is energy you contain. In 1933, physicists saw a high-energy photon vanish as it hit an atom. In its place, an electron and a positron. Light became matter. Run it backward, and matter becomes light. The conversion goes both ways. Pull quarks apart, and energy creates new particles from nothing. There are fields and patterns in fields. Those patterns we call particles. 2,600 years ago, a lodestone pulled iron, and honestly, nobody knew why. The answer, it turned out, was that at the bottom of everything, matter and force and light are all really the same thing, just wearing different shapes. That's where two magic rocks took us. Not a bad run, if you ask me. If you know a wild fact about electromagnetism, Maxwell, or field theory that most people have never heard, drop it in the comments. Some of the best ones, honestly, end up shaping future episodes. You've been watching Guess What I Found Out, the show that follows the question wherever it goes, no matter how strange the destination. If this one was worth your time, subscribe and hit the bell. New episodes come regularly, and the next one is already stranger than you'd expect. See you there, Curious George.